On February 10, 2025, scientists at Rosatom, Russia's state nuclear energy corporation, unveiled a groundbreaking prototype plasma electric rocket engine that has the potential to revolutionize space travel by significantly reducing the duration of missions to Mars. This new propulsion system is claimed to cut travel time to the red planet to an astonishing 1 to 2 months, a dramatic improvement over current travel times that can exceed a year using traditional chemical rocket engines. Overview of the Plasma Electric Rocket Engine. The Plasma Electric Rocket Engine developed by Rosatom utilizes a magnetic plasma accelerator, setting it apart from conventional propulsion systems that rely on the combustion of fuel. The core mechanism involves two electrodes through which charged particles, specifically electrons and protons, are accelerated by a high-voltage electromagnetic field. This method allows the engine to achieve speeds of up to 100 km per second, approximately 62 miles per second. A speed far exceeding the maximum exhaust velocity of traditional engines, which is about 4.5 km per second due to combustion constraints. Key features. 1. Operating mechanism. The engine operates using a pulse periodic mode, generating thrust through the acceleration of charged particles. The magnetic field created by the electrical current propels these particles, resulting in directional motion and thrust. 2. Travel time reduction. With the plasma electric rocket engine, the expected travel time to Mars could be reduced to just 30 to 60 days. This is particularly significant as prolonged exposure to cosmic radiation during lengthy missions poses a substantial health risk to astronauts. 3. Testing facilities. To facilitate extensive testing of the prototype, Rosatom has constructed a specialized 14-meter-long vacuum chamber designed to simulate the conditions of space. This setup includes advanced sensors, vacuum pumping systems, and mechanisms for heat removal to ensure accurate testing of the engine's performance. For initial launch strategy, it is important to note that while the plasma electric rocket engine promises high speeds in space, initial launches will still rely on traditional chemical rockets to reach the spacecraft's designated orbit before activating the plasma system. 5. Projected development timeline. The research team aims to complete a flight model of the engine by 2030, which would pave the way for its application in upcoming Mars missions. Implications for space travel. The development of this plasma electric rocket engine holds significant implications for future space exploration. By reducing the travel time to Mars, the technology not only enhances mission efficiency but also mitigates the risks associated with prolonged spaceflight. The potential for shorter missions could make human travel to Mars more feasible and safe, opening avenues for more ambitious interplanetary exploration. The project has drawn attention to the competitive landscape of space propulsion technologies, with other countries including the United States and members of the European Space Agency also pursuing advancements to reduce travel times to Mars and beyond. This race for faster propulsion systems highlights the growing interest in establishing a human presence on Mars and exploring further into our solar system. Future prospects. As space agencies and private enterprises around the world continue to explore the possibilities of human missions to Mars, Rosatom's plasma electric rocket engine represents a significant step forward. The technology may not only facilitate missions to Mars but could also enable interplanetary travel and potentially journeys beyond the solar system. Conclusion. The unveiling of the plasma electric rocket engine by Rosatom marks a pivotal moment in the field of space propulsion technology. With the capability to drastically reduce travel times to Mars, this innovative engine not only enhances the feasibility of human missions but also addresses critical safety concerns associated with cosmic radiation exposure. As testing and development continue, the anticipated flight model by 2030 could reshape our approach to space exploration, ushering in a new era of rapid interplanetary travel. The information surrounding Rosatom's development of a plasma electric rocket engine presents several counterintuitive points, especially in the context of traditional space propulsion technologies. Below are key counterintuitive insights derived from the content. 1. Speed versus energy source. Typically, rocket engines rely on combustion, which inherently limits their efficiency and maximum speed due to the physical constraints of burning fuel. The novel plasma electric rocket engine, however, operates on electromagnetic fields to accelerate charged particles, achieving much higher speeds up to 100 km per second without the extensive heating associated with combustion engines. This suggests that a more efficient energy transformation can yield greater speeds, challenging the conventional wisdom that faster propulsion requires more fuel. 2. Travel time reductions. The claim that this engine could potentially reduce travel time to Mars to as little as 1 to 2 months is strikingly optimistic. Traditional missions currently take about a year, mainly due to the limitations of chemical propulsion and the need for careful trajectory planning to ensure the safety of astronauts. The radical reduction in travel time raises questions about the viability of human missions and the impact on astronaut health, particularly regarding exposure to cosmic radiation, a concern that traditional missions have focused on mitigating through duration management rather than speed enhancement. 3. Use of chemical rockets for launch. It is interesting that despite the advancements in plasma propulsion, the initial launch into orbit will still rely on traditional chemical rockets. This juxtaposition highlights a crucial transitional phase in space travel technology. Even as new technologies are developed, the reliance on older established methods showcases the challenges of integrating revolutionary technology into existing systems. This reliance also implies that while propulsion technology is advancing, the entire ecosystem of space launch logistics is slower to adapt. For resource efficiency, the plasma engine claims not to require extensive heating of plasma for thrust generation, which is typically a concern in many propulsion systems. The idea that this engine can convert electrical energy into motion with minimal thermal overload offers a counterintuitive perspective on energy efficiency in space travel. This challenges the assumption that high-energy systems must also be high-heat systems, suggesting a new paradigm in propulsion technology. 5. Interplanetary and beyond. The implications of this technology extend beyond Mars missions to potential interplanetary travel and even beyond our solar system. This notion challenges the prevailing view that deep space exploration is a distant prospect, suggesting that advancements in propulsion could radically alter our approach to space exploration timelines and destinations. 6. Radiation exposure management. The reduction of travel time as a method to mitigate radiation exposure during space travel is a compelling argument that contrasts with traditional methods of radiation shielding in mission planning. This approach suggests a shift in focus from passive shielding to active travel time management, which could redefine how future missions are conceptualized and executed. 7. Technological feasibility versus timeline. While the technology promises significant advancements, the timeline for a flight model by 2030 raises skepticism. Historically, many ambitious space technologies have faced delays and challenges that push back timelines. This brings attention to the often optimistic projections made in the field of space exploration, where the path from prototype to operational technology is fraught with practical and technical obstacles. These insights reflect the innovative nature of Rosatom's plasma electric rocket engine and its potential to challenge existing paradigms in space travel propulsion technology and mission planning. The content illustrates that while the technology is promising, it also underscores the complexities and realities of implementing new systems in an established domain. The unveiling of Rosatom's plasma electric rocket engine signifies a pivotal moment in aerospace technology, particularly in the context of interplanetary travel. While several aspects of this development have caught public attention, certain key elements warrant deeper exploration due to their potential implications for space exploration, human safety in space, and the competitive landscape of propulsion technology. 1. Technical innovation overlooked. Plasma acceleration mechanism. Most discussions focus on the engine's ability to reduce travel time to Mars. Yet the underlying technology, the magnetic plasma accelerator, deserves significant scrutiny. Traditional propulsion systems rely on chemical combustion, which limits exhaust velocities to about 4.5 km per second. In contrast, Rosatom's engine accelerates charged particles to speeds of up to 100 km per second. This distinction is not merely a technical specification, it indicates a fundamental shift in how spacecraft could be propelled, potentially leading to innovations beyond Mars missions. The significance lies in the engine's operational mechanism. It uses two electrodes to create a magnetic field that accelerates charged particles, resulting in thrust. This method reduces reliance on large quantities of fuel, which is a critical factor for long-duration space missions. By minimizing the need for onboard fuel during the cruise phase, spacecraft can be designed to carry more scientific instruments, supplies, or crew members, enhancing the mission's overall utility. 2. Human safety and health considerations. Another critical aspect often overlooked is the engine's potential to mitigate health risks associated with prolonged space travel. Current Mars missions, projected to take around a year, expose astronauts to significant cosmic radiation, increasing the risk of cancer and other health issues. By reducing the travel time to just 1 to 2 months, this plasma engine could substantially lower the radiation exposure astronauts face, making human missions to Mars not only more feasible but also safer. Additionally, shorter missions could improve psychological well-being by reducing isolation and confinement, which are significant factors in astronaut mental health during long-duration spaceflights. This consideration is essential as space agencies plan future missions, particularly with an eye towards establishing permanent human presence on Mars. 3. Testing and development milestones. The extensive testing phase planned for the plasma engine involves a specialized vacuum chamber designed to simulate space conditions. This aspect, while mentioned, is crucial for several reasons. Firstly, it underscores the rigorous validation process that new technologies must undergo before being deemed operationally viable. The creation of a 14-meter-long vacuum chamber points to the scale and seriousness of the testing, setting high expectations for performance and reliability. Moreover, the timeline for a flight model by 2030 reflects the urgency and ambition of the project. This timeline is significant as it aligns with other global efforts to advance space exploration technologies. The international space community is on a race to establish a human presence on Mars, and advancements in propulsion technology could play a critical role in determining which nation or consortium leads this charge. 4. Potential for broader applications. While the primary focus is on Mars travel, the implications of the plasma electric rocket engine extend beyond a single mission. The ability to achieve high speeds could enable interplanetary travel to other celestial bodies and even make missions to the outer solar system more accessible. This capacity could pave the way for exploration of asteroids, moons of Jupiter and Saturn, and beyond. Moreover, the technology may also find applications in space tugs for cargo transport, where rapid repositioning of payloads between orbits could become a reality. This versatility could revolutionize not just crewed missions but also commercial space ventures, including satellite deployment and maintenance. 5. Competitive landscape in space propulsion. Lastly, the announcement highlights the competitive nature of space propulsion developments among countries. The global race to reduce travel times for Mars missions is not confined to one nation. Other countries, including the USA and members of the European Space Agency, are also exploring advanced propulsion methods. This competition could spur innovation and investment in the field, leading to faster advancements in technology and potentially more collaborative international efforts in space exploration. In conclusion, the unveiling of Rosatom's plasma electric rocket engine marks a significant leap forward in space propulsion technology. While the immediate implications for Mars travel are noteworthy, the broader significance encompasses human safety, rigorous testing protocols, potential applications beyond Mars, and the competitive landscape of global space exploration. These factors collectively underscore the importance of this development in shaping the future of human spaceflight. Key points for in-depth analysis and discussion. 1. Innovative propulsion mechanism. The plasma electric rocket engine developed by Rosatom utilizes a magnetic plasma accelerator which distinguishes it fundamentally from traditional combustion-based propulsion systems. Unlike conventional engines that rely on fuel combustion, this engine accelerates charged particles, electrons and protons through a high-voltage electromagnetic field. Achieving speeds of up to 100 km per second, about 62 miles per second, marks a significant leap in propulsion technology. This innovation not only enhances the efficiency of space travel but also opens up possibilities for future interplanetary missions, potentially propelling spacecraft beyond Mars and even out of the solar system. 2. Reduction in travel time and associated risks. The potential to reduce the travel time to Mars from nearly a year to just 1 to 2 months is a game-changer for human space exploration. This drastic reduction in journey time could significantly mitigate the risks associated with prolonged exposure to cosmic radiation, a critical concern for astronaut safety. The shorter duration of space missions would facilitate more manageable crew health monitoring and psychological well-being, making human missions to Mars more feasible and safer. The implications of this advancement could also extend to future missions to other celestial bodies. 3. Testing and development timeline. Rosatom has constructed a specialized 14-meter-long vacuum chamber designed to simulate space conditions for extensive testing of the prototype engine. With a power output of approximately 300 kilowatts and an operational lifespan exceeding 2,400 hours. The engine is being rigorously evaluated in its pulse periodic mode to refine its capabilities. The planned timeline indicates that a flight model of the plasma engine is expected to be ready by 2030, which suggests a structured approach to development and testing. This timeline highlights the importance of thorough validation before any actual deployment in space missions. 4. Future applications and competitive landscape. While the initial launch of spacecraft will still depend on traditional chemical rockets, the integration of plasma engines for in-orbit propulsion represents a significant advancement in space travel technology. The research indicates that this technology could also be applied to space tugs for transporting cargo between planets. Furthermore, the competitive landscape of space propulsion technology is evolving, with other countries including the USA and the European Space Agency actively exploring similar advancements. This situation fosters a race for innovation that could lead to breakthroughs in space exploration capabilities and efficiency. Conclusion. The development of Rosatom's plasma electric rocket engine signifies a pivotal moment in space exploration technology. By drastically reducing travel time to Mars and enhancing safety for astronauts, it positions itself as a potential cornerstone for future interplanetary missions. The rigorous testing and development timeline underscores the commitment to safety and efficacy, while the competitive landscape invites further innovation. The implications of this technology extend beyond Mars, hinting at possibilities for exploring more distant celestial bodies and expanding humanity's reach into the cosmos. 1. Project Orion. 1950s to 1960s. Project Orion was a study conducted by the United States during the Cold War to explore the feasibility of using nuclear pulse propulsion for spacecraft. The concept involved detonating a series of nuclear bombs behind a spacecraft to propel it forward. The goal was to achieve rapid interplanetary travel, including missions to Mars, in a fraction of the time required by conventional chemical rockets. Although the project was eventually abandoned due to technical challenges and concerns over fallout, it represented an ambitious effort to leverage nuclear technology for space exploration. 2. NASA's Advanced Concepts for Mars Missions 2000s present. NASA has been actively researching various advanced propulsion technologies to reduce travel time to Mars and enhance mission safety. Concepts such as solar sails, ion propulsion, and nuclear thermal propulsion are being investigated. The goal is to enable faster trips to Mars, ideally within a few months, thereby minimizing the risks associated with long-duration spaceflights such as exposure to cosmic radiation and the psychological effects of isolation. These ongoing studies aim to pave the way for sustainable human presence on Mars in the near future.
3. Ion propulsion systems. Deep Space One and Dawn missions. NASA's Deep Space One mission, launched in 1998, was the first spacecraft to successfully demonstrate ion propulsion in deep space. The spacecraft utilized a xenon ion thruster which provided efficient propulsion over long durations, allowing it to reach its targets faster than conventional methods would allow. Similarly, the Dawn spacecraft, launched in 2007, also employed ion propulsion to visit the asteroid Vesta and the dwarf planet Ceres. These missions showcased the viability of ion propulsion for future exploration missions, including potential expeditions to Mars and beyond, by significantly increasing travel efficiency and extending mission duration. The unveiling of Rosatom's plasma electric rocket engine marks a significant leap in space propulsion technology with ambitious implications for future space exploration. Here are key predictions and outlooks based on current developments. 1. Faster interplanetary travel. The plasma electric rocket engine, capable of propelling spacecraft to Mars in just 1 to 2 months, could revolutionize the timeline of interplanetary missions. This advancement could lead to a new era of space exploration where missions to Mars and potentially other celestial bodies can be completed in a fraction of the time currently required. As a result, we may see more frequent missions, increased scientific research opportunities, and a greater likelihood of successful human colonization efforts on Mars. 2. Enhanced safety for astronauts. One of the most significant advantages of reduced travel time is the enhanced safety for astronauts. The shorter duration of exposure to cosmic radiation, a major health risk associated with long space missions, could make manned missions to Mars not only feasible but also safer. This could lead to a renewed interest and investment in human space exploration, with governments and private entities more willing to fund missions knowing that the risks are mitigated. 3. Development of new spacecraft infrastructure. As the technology matures, accompanying infrastructure such as specialized launch systems, orbital platforms, and cargo transport solutions will likely emerge. The initial phase will still rely on traditional chemical rockets for launch, but as the plasma engine technology proves its reliability, we can expect a shift toward more integrated systems that utilize plasma propulsion for interplanetary travel, possibly leading to the development of space tugs for transporting cargo between planets. 4. Interstellar exploration possibilities. With advancements in plasma propulsion technology, the dream of interstellar travel may become more attainable. Although current designs focus on Mars missions, the potential to extend the application of plasma engines to deeper space missions could eventually lead to exploratory missions beyond our solar system. This could ignite new interest in astrophysics and the search for extraterrestrial life as humanity aims to explore exoplanets and other star systems. 5. Increased international competition and collaboration. As countries like Russia, the USA, and members of the European Space Agency pursue their own advancements in space propulsion, we may witness a competitive environment that drives innovation. This competition could lead to accelerated technological breakthroughs but may also foster collaboration on international projects. Global partnerships could emerge, aiming to pool resources and expertise for ambitious missions to outer planets or asteroids. 6. Investment in research and development. The success of the plasma electric rocket engine prototype could stimulate increased investment in space technology. Governments and private companies might allocate more funds to research and development, paving the way for innovations in materials science, energy generation, and sustainability in space travel. This influx of investment could also lead to technological spillover benefits in other industries, including telecommunications, materials engineering, and renewable energy. 7. Public interest and support for space exploration. As news of breakthroughs like the plasma electric rocket engine spreads, public interest in space exploration may grow. This could lead to increased support for funding space programs and initiatives.
Educational programs focusing on STEM science, technology, engineering, and mathematics might gain traction, inspiring the next generation of scientists and engineers to contribute to future space missions. 8. Potential environmental considerations. With advancements in space propulsion technology, there may be opportunities to design systems that are more environmentally sustainable.
Plasma engines that utilize hydrogen as fuel could lead to less waste and pollution compared to traditional chemical rockets.
Future designs might prioritize sustainability in both launch and operational phases, which could align with global environmental goals.
Conclusion. Rosatom's plasma electric rocket engine is poised to reshape the landscape of space exploration.
By significantly reducing travel times to Mars and potentially beyond, enhancing astronaut safety and driving technological innovation. This development could mark the beginning of a new chapter in humanity's quest to explore the cosmos. As we venture further into the 21st century, the possibilities for interplanetary and even interstellar travel will continue to expand, driven by advancements in propulsion technology and human ingenuity.